Okay, this is the last of our hypothesis testing, I think, for first year further. In fact, I think this is the end of statistics, although I do need to check my scheme of work. So contingency tables, you'll probably have to pause the video a bit to copy stuff down because I've pre-prepared some of it. So contingency tables, we're basically looking at two-way tables. So we've got school X, school Y, A-level grades. So if you're looking at the two schools and deciding whether your child should go there, you might be interested to know whether there's an association between the school and the grades achieved. And because the sizes are different, it's not always totally obvious by just looking at the numbers, so to speak. So this is a contingency table, and like matrices, we can describe them as rows by columns. So this is a 2x4 contingency table. So we're going to test 5% significance level. Is there an association between grade and school? So null hypothesis is that the school and grade are independent. So what school you go to does not affect your grade. Although we're not looking for causation here, actually, we're just seeing if there's any association in the data. School and grade are not independent is the alternative hypothesis. So if you recall from our probability work, if we've got events A and B, which are independent, then our test for independence is that the probability of A times the probability of B is equal to the probability of being in the intersection of A and B. And if that's true, they're independent. So those two statements are equivalent. So I'm going to start actually over here, because like with the binomial and Poisson ones you've been doing, if the expected value is below 5, we need to combine columns, or you could combine rows. So coming into this one here, I'm just going to check that expected value first so that we can combine columns if necessary. You can see where this is going, can't you? So if I do the probability of school X, so the probability of being in school X times the probability of getting a grade of D. So the probability of school X is 50 out of 120. And then the probability of getting a grade D is 5 over 120. And when you multiply this together, if they're independent, this is the probability of being here. So that gives us 50 times 5, which is 250 over 120 squared. And so the expected frequency for this one here, so that's the probability of being there, is equal to 250 over 120 squared times by the total. So this is going to cancel here, and we end up with 250 over 120, which is 2.08, which is less than 5. So I am going to have to combine together. It wouldn't make sense to combine the two schools together. And I think I'm right in saying with the Edexcel questions you're always combining columns. So it makes sense to combine these two grades together instead. Just coming back into this calculation here, this 250 was 5 times 50. So it's the total on the column times the total on the row divided by the total number of students. And that method will work wherever you are in the table, but it comes from here and then timesing by 120, just so you understand where that process is coming from. So that's below 5, so you need to combine rows or columns as appropriate. So on the next one, I've set it up pretty much. Sorry, I might have to copy this down a little bit in your own time. So it's C or D, 17 plus 3 is 20, total 50 still, 30 plus 2, 32, and then 47 plus 5 is 52. Takes us to 120. So then to get a table of expected values, let's check that's lined up. We follow the same process. So for this first one, you do the column total, which is 44, times the row total, which is 50, or vice versa, and then you divide by the grand total of 120, and that gives you, I've got it here, 18.33. This is a slightly adapted version of your online example actually. So expected frequency, row total times column total over grand total. So here I'm doing the row total. I think you normally do the rows first, but it doesn't really matter. So 50 times 24 over 120, which gives you 10. And then for this one, it's 50 times 52. And that gives you 21.67. And then you can do the same here. So you can do 72 times 44. Which is 25.67. But because you know the totals, you could actually just subtract it. So 24 minus 10 is 14. 52 minus 21.67 is 30.33. So you could use the totals instead. And then the rest is quite similar to what you're doing before. The degrees of freedom, because this value here is determined by this total, and in a sense this value here is determined by this total, then, so these will all add up to 70, then the degrees of freedom is the number of rows minus 1 times by the number of columns minus 1. So that's going to be the same for all contingency tables. So for this one here, the number of rows is 2 minus 1 is 1, And my number of columns after I've made that adjustment is 3 minus 1 for the degrees of freedom, which is 2. So my degrees of freedom is 2. If we're testing at a 5% significance level, then the critical value, so reading off of the table like you did before, comes out as being 5.991. And then to calculate your test statistic, which is denoted with capital X squared, it's the same process. I'll write it out. So it's observed minus expected squared divided by the expected, and you just have to be careful not to make any errors. So observed minus expected squared over expected. There's a lot of number crunching again. So 26 minus 25.67. And the fit's not looking bad if you compare the two. And then 12 minus 14 squared over 14. And then 32 minus 30.33 squared over 2.33. If you chuck all that into a calculator, you should get 0.9165. She says with confidence. And then that is comparing with the critical value, which is 5.991, and it's less than 5.991. So if you remember, the chi-squared curve, without worrying too much, is doing something a bit like that. We've got this critical value over here, and that area there's 5%, and we're very close to 0 here, really, aren't we? So we're kind of here somewhere at 0.9165. So the observed is close to the expected, and so we can accept the null hypothesis. So the null hypothesis is that the school and grade are independent, so the data is fitting that really well. So there is insufficient evidence to suggest an association between school and grades of pass, or you could word that as the school and grades of pass seem to be independent. So you're not looking for causation here. That's the other thing just to be a little bit wary of. So yeah, we're just looking to see whether there's an association between two things. So a bit like with the correlation, you're not saying that correlation implies causation. So yeah, just be a little bit wary of that as well. So you can use your textbooks that are in the cupboard today, yay. So you've all got a book in the cupboard with your name on it, I believe. And there's a few questions in there which are absolutely fine. So it's exercise 4.1, page 79, question 2, question 12 and question 14. And yeah, it should definitely see Friday. So yeah, thanks for staying with me this week. And any questions, just ping me a message and I'll try and sort that out for you. But hopefully that's explanatory enough. There's the bottom of the board.